Hey everyone, Linus here. Today we're diving deep into the world of graphics cards, those magical pieces of silicon that bring our digital worlds to life. In the simplest terms, a graphics card is like a dedicated brain for visuals inside your computer. It takes data from the CPU, processes it at lightning speed, and transforms it into the images you see on your monitor. Without a graphics card, your computer would struggle to display anything beyond basic text and colors. Imagine trying to play the latest AAA game with just your CPU handling the graphics. It would be a slideshow. That's because CPUs are designed for general-purpose tasks, while GPUs, the brains of graphics cards, are built specifically for handling the complex calculations required for real-time image rendering. From the smallest indie game to the most demanding Hollywood CGI production, graphics cards play a crucial role in shaping our visual experiences. But how do they actually work? Well, buckle up because we're about to explore the fascinating world of GPU architecture, graphics pipelines, and the technologies that power the stunning visuals we see today. Get ready to learn about cores, shaders, and all the cool stuff that makes graphics cards tick. By the end of this deep dive, you'll have a whole new appreciation for the powerhouses that bring our digital worlds to life. Alright, let's crack open the hood and see what makes these graphics cards tick. At the heart of every GPU are three key components: cores, VRAM, and shaders. Think of cores like the workers in a factory, each capable of handling a small task. GPUs have thousands of these cores, allowing them to process massive amounts of data simultaneously. This is what gives GPUs their parallel processing power, making them ideal for handling the millions of calculations needed to render complex images. Next up, we have VRAM or video RAM. This is like the GPU's dedicated memory bank, storing all the textures, models, and other graphical data it needs to access quickly. The faster and larger the VRAM, the more detailed and complex the graphics a GPU can handle. This is why high-end graphics cards boast tons of superfast VRAM to keep up with the demands of the latest games and applications. Finally, we have shaders. These are small programs that run on the GPU cores, dictating how light, shadows, and colors are applied to objects in a scene. Shaders are responsible for creating all the visual effects we see in games and movies, from realistic reflections to explosive particle effects. The more advanced the shaders, the more realistic and immersive the graphics will be. Together, these three components, cores, VRAM, and shaders, form the backbone of modern GPUs, enabling them to process vast amounts of graphical data and render stunning visuals in real time. But understanding the individual components is just the beginning. To truly appreciate how a graphics card works, we need to understand how these components come together in the graphics pipeline. Now that we know the key players, let's talk about how they work together to bring images to your screen. This is where the graphics pipeline comes in. Think of it like an assembly line, where each stage performs a specific task to transform raw data into a final image. The journey begins with vertex processing. Here, the GPU receives a bunch of vertices, which are basically points in three-dimensional space that define the shape of an object. The GPU then crunches some numbers to figure out where these vertices should be positioned on your screen, taking into account the camera angle, object movement, and other factors. Next up, we have rasterization. At this stage, the GPU takes those processed vertices and turns them into a grid of pixels, which are the tiny squares that make up the image on your screen. Essentially, the GPU is figuring out which pixels need to be filled in to represent the object on the screen. Finally, we reach pixel shading. This is where the magic really happens. The GPU applies shaders to each pixel, determining its color, brightness, and other visual properties based on lighting, textures, and other factors. This is where the GPU flexes its muscles, using its thousands of cores to perform complex calculations for each pixel on the screen. This entire process, from vertex processing to pixel shading, happens incredibly fast, multiple times per second, to create the illusion of motion. The speed at which the GPU can complete this pipeline determines the frame rate, which we'll talk about more in a bit. But first, let's explore the diverse world of GPU workloads beyond just gaming. When people think of graphics cards, they often think of gaming, and for good reason. GPUs are the driving force behind those stunning visuals and immersive experiences we crave in our favorite games. But the applications of GPUs extend far beyond the realm of entertainment. Their ability to process massive amounts of data in parallel makes them ideal candidates for a wide range of tasks, collectively known as GPGPU or general-purpose GPU computing. One of the most impactful applications of GPGPU is in the field of artificial intelligence. Training AI models, especially deep learning models, requires crunching through massive data sets, and GPUs excel at this task. Their parallel processing capabilities significantly accelerate the training process, enabling researchers and developers to create more powerful and sophisticated AI algorithms. But it doesn't stop there. GPUs are also making waves in scientific research, financial modeling, video editing, and even cryptocurrency mining. From simulating protein folding for drug discovery to rendering complex architectural visualizations, GPUs are becoming indispensable tools across various industries. The key takeaway here is that GPUs are no longer just for gamers. Their ability to handle massive amounts of data in parallel opens up a world of possibilities across diverse fields, making them one of the most versatile and powerful components in modern computing. Section 5. The need for speed parallelism and memory bandwidth. We've talked about how GPUs excel at handling massive amounts of data, but what makes them so good at it? The answer lies in two key concepts: parallelism and memory bandwidth. Parallelism, in simple terms, means doing lots of things at once. Unlike CPUs, which excel at handling tasks sequentially, GPUs are designed to perform thousands, even millions of operations simultaneously. Think of it like this: if you need to move a mountain of sand, one grain at a time would take forever. But if you had thousands of tiny shovels working together, you could move that mountain much faster. That's the power of parallelism, and it's what allows GPUs to render complex images with incredible speed. But parallelism alone isn't enough. The GPU also needs to access the data it's processing quickly and efficiently. That's where memory bandwidth comes in. Think of memory bandwidth as the width of the highway connecting the GPU to its VRAM. A wider highway means more data can travel between the GPU and its memory at the same time, preventing bottlenecks and keeping those cores fed with information. High memory bandwidth is crucial for GPUs because they often need to access massive amounts of data like textures and models to render a single frame. Without sufficient bandwidth, the GPU would be starved for data, leading to slowdowns and stuttering, especially in graphically demanding applications. In essence, parallelism and memory bandwidth are the two pillars of GPU performance. They work hand in hand to enable GPUs to crunch through mountains of data and bring our digital worlds to life with stunning speed and fidelity. Section 6. Real-time rendering, the quest for smooth visuals. Now, let's talk about real-time rendering, the bread and butter of GPUs. In simple terms, real-time rendering means generating images fast enough to give the illusion of motion, like what you experience when playing a video game or interacting with a three-dimensional application. This requires the GPU to process and render a new image multiple times per second, typically 30 to 60 times or even more for smoother experiences. The speed at which the GPU can complete this rendering process is measured in frames per second, or FPS. Higher FPS means smoother, more responsive visuals, while lower FPS can result in choppy gameplay and a less immersive experience. This is why gamers strive for high frame rates, as it significantly impacts the overall enjoyment and responsiveness of games. Achieving high frame rates in real-time rendering is a delicate balancing act. The GPU needs to handle complex calculations for each pixel on the screen, multiple times per second, all while managing memory bandwidth and staying within thermal limits. This is where the power of parallelism, efficient architecture, and clever optimization techniques come into play. Game developers and GPU engineers are constantly pushing the boundaries of real-time rendering, developing new techniques and technologies to create ever more realistic and immersive experiences. From advanced lighting models to physics simulations, the quest for smoother, more realistic visuals is a never-ending pursuit in the world of computer graphics. Section 7. A glimpse into the future, ray tracing and DLSS. Speaking of pushing boundaries, let's talk about some cutting-edge GPU technologies that are revolutionizing the world of computer graphics, ray tracing, and DLSS. Ray tracing is a rendering technique that simulates the physical behavior of light, resulting in incredibly realistic reflections, refractions, and shadows. Traditionally, achieving realistic lighting in games involved a lot of trickery and approximations. But with ray tracing, the GPU can actually trace the path of individual rays of light as they bounce around a scene, resulting in a level of realism that was previously impossible to achieve in real time. However, ray tracing is incredibly demanding, requiring massive amounts of processing power. That's where DLSS comes in. DLSS, or Deep Learning Supersampling, is an AI-powered technology that leverages the power of deep learning to upscale images to higher resolutions while maintaining incredible detail and clarity. In essence, DLSS allows the GPU to render the game at a lower resolution, which is less demanding, and then use AI to upscale it to your desired resolution, all while maintaining or even improving image quality. This frees up valuable GPU resources, allowing for higher frame rates and more complex effects, even with ray tracing enabled. Ray tracing and DLSS are prime examples of how advancements in GPU technology are pushing the boundaries of what's possible in computer graphics, paving the way for even more realistic and immersive gaming experiences in the future. Section 8. Taming the heat, cooling and powering the GPU beast. All this processing power doesn't come without a cost. GPUs generate a significant amount of heat, especially under heavy load. This is why modern graphics cards come equipped with elaborate cooling solutions, typically involving heat sinks, heat pipes and fans to dissipate heat and keep the GPU operating within safe temperatures. Heat sinks are large metal blocks designed to absorb heat from the GPU die. Heat pipes then transfer this heat away from the heat sink to a fin stack where it can be dissipated by fans. The more powerful the GPU, the more robust the cooling solution needs to be to prevent thermal throttling, which is when the GPU reduces its performance to avoid overheating. Along with cooling, power delivery is another crucial aspect of GPU design. GPUs require a significant amount of power to operate, often drawing hundreds of watts under load. This power is supplied through the PCIe slot on the motherboard and often supplemented by dedicated power connectors from the power supply. Ensuring adequate power delivery is essential for stable GPU operation. Insufficient power can lead to instability, crashes, and even damage to the graphics card. Therefore, it's important to choose a power supply that can handle the power requirements of your graphics card, especially if you're planning to overclock it for increased performance. Section 9. The software symphony drivers and GPU optimization. Finally, let's talk about the often overlooked heroes of the GPU world: software and drivers. While the hardware is undoubtedly important, it's the software that acts as the conductor, orchestrating the complex symphony of data processing and rendering that brings our digital worlds to life. Drivers are pieces of software that act as intermediaries between the operating system and the GPU, enabling them to communicate effectively. They contain instructions and optimizations specific to the GPU model, ensuring that it operates at peak performance and compatibility with various applications. Keeping your drivers up to date is crucial for optimal GPU performance. New driver releases often include performance improvements, bug fixes, and support for the latest games and technologies. Conversely, outdated or incompatible drivers can lead to performance issues, crashes, and graphical glitches. Beyond drivers, game developers also play a crucial role in optimizing their games to run smoothly on different hardware configurations. They employ various techniques such as level of detail adjustments, shader optimization, and efficient asset utilization to ensure that their games run smoothly on a wide range of systems. In essence, while the hardware lays the foundation, it's the software, from drivers to game optimization, that unlocks the true potential of a graphics card, enabling it to deliver those stunning visuals and immersive experiences we crave.